Hello, this podcast is on momentum and impulse. Specifically, we're going to learn about momentum, the conservation of momentum, impulse, and the impulse momentum theorem. Newton considered an object's momentum its quantity of motion. It is also referred to as moving inertia, a measure of how hard it is to get a moving object to speed up, slow down, or change direction. I also had a student of mine once say that momentum is the power of an object's motion. The mathematical definition of momentum is the momentum is equal to the object's mass times its velocity. Notice velocity is a vector quantity and mass is a scalar, so this is a scalar multiplication of a vector and it gives us a vector quantity. So momentum is a vector quantity with units of kilogram meters per second. Let's look at an example of calculating momentum. Which has more momentum? A 100 kilogram running back moving at 8 meters per second or a 150 kilogram defensive tackle running at 5 meters per second? We'll go ahead and do the calculations and we can see that the running back has a momentum of 800 kilograms meters per second and the defensive lineman has a momentum of 750 kilogram meters per second. So in this case, the running back has more momentum. It just goes to show you that the larger object does not always have more momentum. Let's talk about what causes momentum to change. We can use Newton's second law of motion to see that the rate at which an object's momentum changes is equal to the net force acting on the object. And here we'll go ahead and take dp dt, that's the rate at which momentum changes, and we can express the momentum as mass times velocity. Using the chain rule, this gives us v dm dt plus m dv dt. We're going to assume that the object's mass doesn't change with time, and that leaves us with the rate at which momentum changes is mass times dv dt. dv dt is simply the definition of acceleration, so we can substitute acceleration in there, and we get mass times acceleration, and we know from Newton's second law that that's equal to the net force. The rate at which momentum changes is equal to the net force. And let's think about that conceptually. We know that momentum has to do with the movement of the object. It's a quantity that describes its motion. And we know that a net force causes change in motion. So it would make sense that the object's momentum is going to change more when there's a larger net force applied to it. Let's look at an example. An object's momentum increases uniformly from 10 units of momentum to 50 units of momentum over 2 seconds. What was the net force acting on the object? To do this, we're simply going to look at the change in momentum divided by the change in time. That'll give us the rate at which momentum was changing, and that will be equal to our force, and we can see that it's equal to 20 newtons. Momentum is a conserved quantity, so we have the law of conservation of momentum. And let's take a look at why that exists. In the previous section, we learned that the net force is equal to the rate at which momentum changes, dp dt. We can use this relationship along with Newton's third law of motion to conclude that the system's momentum is conserved unless a net external force acts on it. First, let's take a look at a system of two particles A and B that are in contact with each other. We draw the force diagrams for each and we can see that B is exerting a normal force on A and A is exerting a normal force on B. From Newton's third law, we know that these two forces are action-reaction forces, so they're equal to each other but in opposite directions. We can take this into what we learned in the previous slide and we can say that the rate at which A's momentum changes is equal to the normal force B exerts on A, and similarly we can say that the rate at which B's momentum changes is equal to the force that A applies to B, but through Newton's third law we know that that is negative the force that B applies to A. So notice that the rate at which A's momentum changes is equal to the normal force of B on A, and the rate at which B's momentum changes is equal to negative the force of B on A. So we can go ahead and find the rate at which the system's momentum changes, and to do that we just add up the individual momentum rates, the rate at which A's momentum changes plus the rate at which B's momentum changes, and that's going to be equal to the normal force of B on A plus negative the normal force of B on A, and of course these two cancel out to equal 0, and that tells us the rate at which the system's momentum changes is 0, which means the momentum doesn't change. The law of conservation of momentum is very important. It's one of the most important laws that governs the interaction between particles or systems of particles. In fact, it's more important than Newton's 3 laws of motion. We're going to move away from momentum for a few minutes and talk about impulse. Impulse is the application of a force to an object for an amount of time. Its mathematical definition is I, the symbol for impulse, is equal to the integral of f dt evaluated from the initial time to the final time. It has units of newtons, seconds, which is the same as kilogram meters per second. Note, these are the same units as momentum, and this will be very important later on. If force is constant, then calculating impulse is very straightforward. It's simply the force times the amount of time that that force was applied. Here's an example. John pushes a box with a force of 50 newtons for 10 seconds. What is the impulse applied to the box? Since F is constant, we can use this formula. We find out that the impulse is 500 newton seconds. Well, of course, life can't always be this simple, so let's explore impulse with varying forces. When forces are variable, we must use the integral form of the impulse equation. And if we're given an equation for force as a function of time, we just need to solve the integral. For example, an increasing force is applied to an object for 5 seconds. The force varies with time according to the equation F equals 20 plus 5t, where F is in newtons and time is in seconds. What is the impulse applied to the object? We need to set up our integral. The impulse is equal to the integral of f dt evaluated from 0 to 5 seconds. We're going to substitute our expression for the varying force, and we're going to integrate that expression, and we come up with 162.5 newtons per second. We don't always have an equation to express how force varies, so if we don't have that force as a function of time, we can graph force versus time and find the area under the curve. And let's take a look. So here's a plot of force versus time. And if we break into thin rectangular strips of width delta t sub I and height f sub I, that area of this strip represents the impulse for this time segment. If we take all of these thin strips and add up their areas, we'll wind up with the area under the curve, and it'll be equal to the impulse. So how do we calculate the area under the curve? Well, sometimes, especially if the force timeline is a straight line with a positive or negative slope, it's easy to calculate the area. Other times we may have to plot the data in LoggerPro, and it can find the area under the curve. You can plot your data in a graphing calculator and find the area under the curve, or you can use numerical integration techniques such as the trapezoid method or Simpson's method. Let's take a look at an example here. A force is applied to an object for 10 seconds as shown in the graph below. What is the impulse applied to the object? Well, this force time graph is pretty straightforward. It consists of a constant force segment and then an increasing force segment. This we can simply find the area under the curve, and of course that's equal to the integral from 0 to 10 of f dt, and that's our definition of impulse. So if we find the area under the curve, we will have our impulse. And we can take this area and break it into a rectangle and a triangle and find the areas of those, and in this case we're left with an impulse of 260 newton seconds. The final way we can calculate impulse when we have a varying force is by using average force. So the variable force can be represented as an average, and in that instance the impulse is equal to the average force times delta t, or another expression for that, the average force is equal to the impulse divided by delta t. And if we just take a look at this graphically, here's our varying force. The area under this curve is equal to the impulse. If we know the average force, we can plot that versus time, and of course the average force is constant over this time period, so we're left with a rectangle. The area of this rectangle, as you can see, is equal to the area under the force versus time curve. Let's look at an example. What is the impulse if an average force of 75 newtons is applied to an object for 6 seconds? We go ahead and just use our formula. Impulse is equal to the force times delta t, and we find out that the impulse applied to the object was 450 newtons seconds. Let's make an important connection between impulse and momentum, and that'll lead us to a very useful problem-solving tool called the impulse-momentum theorem. This theorem states that the impulse applied to an object is equal to its change in momentum. Let's prove that. We have our definition for impulse. It's the integral of f dt. We can use Newton's second law to make the substitution mass times acceleration in place of the force. And then we can use the definition of acceleration to substitute dv dt for acceleration. And when we do that, we wind up with impulse is equal to the integral of mass dv. Assuming mass is constant, this integral is equal to the change in momentum. This is our basis for the impulse-momentum theorem, which, if you think about it, it makes a lot of sense conceptually. We know that applying a net force for a period of time to an object changes its motion, so it would make sense that it also changes its momentum, and the amount in which the momentum changes is equal to the force times how long you apply that force. Let's take a look at an example here on how we use the impulse-momentum theorem. A batter impacted a baseball for 0.05 of a second with a force of 300 newtons. The ball was traveling 40 meters per second before it was hit. What was its velocity leaving the bat? And the ball has a mass of 0.15 kilograms. In this problem, it doesn't say if this force is a constant 300 or an average 300, but we're going to treat it as if it's one of those. So in this case, our impulse is going to be equal to the force times delta t, and we know that that's going to be equal to the change in momentum. Well, the mass of the baseball is not going to change while it's being hit, so our change in momentum is going to be mass times, in parentheses, v sub f minus v sub I. We can go ahead and rearrange this expression to find v sub f, and we're left with this rearranged equation. We plug in our known quantities, and if the baseball was coming into the batter, and we consider that the negative direction, then the baseball is going to leave the bat in the positive direction at 60 meters per second. This wraps up our concepts on momentum and impulse, but let's just summarize what we've learned. Momentum is the quantity of motion, and it's equal to the mass times the velocity, and momentum is a vector quantity. Momentum is also a conserved quantity when the net force acting on the particle is 0. The rate at which a particle's momentum changes is equal to the net force applied to that particle. Impulse is a quantity that's the application of a force for a period of time. Impulse is equal to the integral of f dt. Finally, the impulse-momentum theorem states that the change in momentum is equal to the impulse applied to the particle. This fundamental equation is often rearranged to this form to become a useful problem-solving tool. Well, that ends our podcast. I hope this helped you understand the concepts of momentum and impulse, and have a good day.